Okay, so this is discrete mathematics, the mathematics of scheduling, which is section 8.1 and 8.2 in our textbook. To begin, we have the basic elements of scheduling. We see that our vocabulary here starts with processors. So processors are the workers that complete the tasks for completing our project. The workers or the processors may be human or mechanical. They could be robots, they could be animals, they could be computers, anything that can get a job done for us. After that, we have tasks. Tasks are the individual pieces of work that make up the completion of the project. So for this unit, we're going to restrict the definition of a task to be an indivisible unit of work that is carried out by a single processor. Tasks have 4 states that they can be in. If a task is ineligible, that means the task cannot be started right now because there are other requirements that must be met before starting the task. These are usually other tasks. For example, you can't start to construct a roof if the foundation isn't even done. You need the foundation and the walls of a house before you can construct the roof. So that's what we mean by ineligible. If a task is ready, that means all preceding tasks have been done and it can be started at any time a processor is freed up. And if a task is executing, that means that it is currently being carried out. And then there's completed. That means the task is done and the processor is free to move on. Processing time is the amount of time that it takes to complete a task by one processor. It is assumed that all processors can complete the task in that stated time. We do not say that some processors can work faster than others. That might be a real world scenario, but for the case that we're considering, all processors complete the task in the same amount of time. And then precedence relations. This describes the order in which a task must be completed. And here's my example again with the house. The foundation precedes putting up the walls precede putting up the rafters precede putting up the roof. So these are preceding tasks, things that must be done before you can move to that step. Okay, so here we have a precedence table. This precedence table gives us our task lists over here, tasks A through G, and then the next column is the amount of time it takes to complete each of those tasks. You'll see here that A is paired up with 3, and in the graph, A has a 3 next to it. That 3 is the amount of time it takes to complete task A by a single processor. So we have our list of tasks here, and then we have preceding tasks. So we see that A has no preceding task. That means it has nothing that comes before it. A can be started right away. Notice that start has a time of 0. There's no amount of time needed to start a job. It is once it has begun, these 3 tasks are immediately able to be selected by a processor, and that's why those 3 tasks have nothing in this part of their table. Once task A is done and task G is done, then we see that task D requires A, F, and G before you can start it. So if just task A were done and task F were done, that would not be enough to start task D. You still need task G to be done. All 3 of them are required. So looking back at this, here is our table of precedence relations, and this is the project digraph. It tells us, you'll see the arrowheads, tells us the direction of flow of work that we're doing. So we went from start to task A, and from task A, we can go on to task B or task D, but D cannot be started unless G and F have already been completed, because we see that they all feed into here. And we will talk about how to draw these digraphs in a later slide. Okay, so talking about digraphs, there are parts of digraphs we have to become familiar with. When we say digraph, that's just short for saying directed graph. It's the same thing, it's just a shorter way of saying directed graph. The digraph means that the edges have direction. And once we say that, that means there is an arrowhead on the edge. And once we give an edge an arrowhead, we no longer call them edges, but instead we call them arcs. So that is the new vocabulary for edges when we're talking about digraphs. And then we have some statements here because we want to know what it means to be incident to or incident from. So in this drawing, arc xy, you can say that x is incident to y because you travel from x to y, or you can say y is incident from x because the arrow comes from x to get to y. So it is the order that you start stating the letters as to whether you use the word to or from. Going from x to y, or I'm at y coming from x. The next phrase is adjacent to, and in this image we can see that where one arc ends and the next arc begins is the key to understanding adjacent with digraphs. We can say that RS is adjacent to AR because RS starts where AR ends. So RS is adjacent to AR. We do not say AR is adjacent to RS. That would be wrong. All right, so the next vocabulary here is in degree and out degree. And we can see that the in degree is the number of arcs that end at a vertex. So over here, we're looking at vertex D. If you find D, it's right here. You say how many arrowheads are coming into D? Well, there are 3 arrowheads coming into D. That's why it has an in degree of 3. If I asked you what was the out degree of vertex D, you would say 1 because it only has 1 arc coming out from it. The next one is vertex C. You would find vertex C and then say how many arrowheads are coming into C. Let me get my eraser here. And we see that looking at vertex C, there are 2 arrowheads coming into it, which is why it has an in degree of 2. Next is out degree, and if you look at vertex A, you say how many arrows are leaving out from A, and you should see that there are 2 coming out from A. There's 1 coming into A. If we ask the in degree of A, it would be 1. And then the last example is B. If we find vertex B, we see that vertex B has an out degree of 1 because there is only 1 arrow leaving from vertex B. So those are our in degrees and our out degrees of a vertex in a digraph. All right. And our last slide is how do we draw a digraph from a precedence table? And we can see here that we start with the empties. Anything that has an empty precedence is going to be connected to a vertex that we call start. So let's start by drawing our start vertex. And we're going to draw an arrow that goes to a vertex we'll call A. We'll draw an arrow out to a vertex that we call F, and an arrow out to a vertex we call G. So these have been put into our digraph. We cross them out. And now we say I'd like to draw vertex B. I can do that because it only needs vertex A. So I draw out my vertex B. Done. Next is vertex C, which comes from B and D. I don't yet have a D in the drawing, so I'm going to come down to D and say, can I draw that yet? I see that I have to go from A, F, and G. A, F, and G comes up to a vertex that we call D. And now I can draw vertex C because it needs B and D. And lastly, vertex E comes from F. And I should be putting the numbers next to each of these tasks. This will benefit us later when we're scheduling. All right, and the last step is these last vertices here need to go to a vertex that we call end. So we've ended the project. Okay. And that's it to drawing a digraph. We used a table to help us identify precedence tasks as we draw new tasks and we connect them. All right, so you should be able to finish the chapter section 8.1 and 8.2 vocabulary and questions related to these topics.